Good morning and welcome to Stockholm. Maybe I shouldn't say good morning because I understand that some of you are all across the globe and some at the Pacific Ring. So to you, a good afternoon, good evening, and also some in Brazil. So maybe a too early morning. My name is Patrick Alfredson. I will be your host during this hour where I will try to walk you through this field of life cycle management and what it means to shoulder through life responsibility. As you see here, I'm a doctor in mathematics and I've been with Sister Connor for 26 years. So I spent basically my entire professional career trying to sort out this question, providing tools, methodology, analysis to help organizations and projects to get a clear grip on what it means to take on this journey. Before we start, I have some information which could be interesting to you. The webinar will be recorded, so you can request the video recording after the presentation is complete. We will not hand out the slides, but if you want them, please contact us and see if we can sort something out. We kindly invite you to ask questions. There is a Q&A functionality available. So you can type in your question and hopefully have a chance to, after the webinar is closed, to comment on some of the questions. We'll see how much time we have left, but hopefully some time for that. There are also different resources and links available, so you can browse and click on them and see if you find other information that could be of interest to you. And just a brief agenda. I will start the webinar with some kind of theory or mindset trying to illustrate what is meant by life cycle management. What is the vision? What's the heart and mind? What is it that we want to achieve? Not to make that too theoretical, then I will also provide two examples or two illustrations for what this could mean in practice through two case stories to which I have been involved in and provide some illustration for what this mindset means in practice and how you should try and grasp this field. So let's begin. When I meet with new people and I try to illustrate what is it that we do, I often start with this picture, which I would like to call the hearts and minds of life cycle management, or the vision over the overarching objectives. And it's quite straightforward. We want to form, develop, and sustain cost-effective systems. And in our case, systems that are reliant on technical components. It's material assets that we want to form, develop, and sustain cost-effectively. And by effective, of course, we mean that these systems should be able to provide to us what we want from them, to satisfy the need, to deliver value, or to be productive, in some way to be valuable to us or to the society or to us as an organization. But cost-effective also means that we must control and understand what are the cost implications associated with these systems. Of course, naturally, what does it cost to create this functionality, this capability, these systems that we want? But equally important, what will it cost us to really keep up the functionality within these systems, the capabilities over time, to operate and maintain or sustain these systems over time? And when you present this picture to an organization or a manager, he says, well, of course, this is so obvious. So of course we sign into this. This is what we want. And this, in many cases, also say, this is what we do. But then that is when it becomes interesting. Is it really, do you really take on all the aspects of this question or this ambition within your organization? So what does it mean for a system to be effective? The term used for this is often system effectiveness. And clearly what most engineers and most managers interpret as natural is the technical performance element of effectiveness. The system must be capable to meet the need. There are technical functional requirements placed on the system that it must reach. If we cannot drive fast enough, if we cannot deliver if we cannot reach a certain technical level, we are not meeting the technical requirements. But equally important is the fact that we need the system there and available, ready in a certain condition, in a required condition to meet the need. If the system is in maintenance, if the system is degraded, so we cannot do with the system what we hope to do, well, then the system is not really effective. Potentially it could do it, but currently it can't. So there are a lot of availability related requirements placed on the system, and this is of course equally important. Another factor is that, of course, to be able to reach, to get the value from the system must be delivered. It must be there, it must be in place. So sometimes a program can be very disturbed by delays in the delivery of the system, the delays in the delivery of a capability, to such degree that it almost brings the system or the program to death. So, of course, available also means that you must have it there. We cannot wait 5 more years, so we cannot be delayed. So these are very important elements of really being effective. Another factor sometimes, which could be critical for some system, is that we must ensure that we can safely meet the need. There are system safety related requirements placed on the system. And of course, there could be other factors. So there are a lot of factors that really describe what the system needs to be to be effective, to be useful to us, and to be able to deliver what we need from the system. Another important factor is this need, which I have introduced here. Well, what do we need to be able to do with the system? The need describes some level of ambition, some operation requirements that are placed on the system. And of course, the more we want from the system, the more we want the system to be able to conduct or perform, of course, the more value we get from the system. But you must be very careful here, because if you want too much and don't understand the complementary aspect, the cost of the system, because you could wish, but you must also understand that with every ambition, there is a cost. And we must understand, if we want the system to be operating to meet these type of operation requirements, we must also understand what cost, what budget are we then assigning to the system. So the second element, the second part of the equation is the cost side. Of course, we want to get the value, but we must understand what is the cost involved in reaping or receiving this value from the system. And the natural view to take on cost is the through life cost picture, or the total cost picture over time. It's often expressed as the life cycle cost associated with the system over its intended system life cycle. And of course, that covers the initial costs required to set up the system, to enable the system, the initial investments and costs. But equally important, the costs over time, over the system life cycle, to operate, maintain, support, sustain, and many times reinvest in the system. Because there could be parts that quickly become obsolete, there could be end of life in certain aspects, certain elements of the system, and we must not neglect that there might be different technical life length in various components of the system. And we must understand that we need to take on the responsibility to reinvest in the system when the system is degraded, when the certain elements are end of life. So the total cost could involve many types of cost elements. And they should all be assessed and covered in this total cost picture. As I already indicated, the cost associated with the system it's not a given. It depends highly on what you want the system to be able to perform. Depending on the level and the scope and the operational requirements and the ambition you place on the system, you also drive the costs. So the more technical functional requirements you impose, the higher you place them, the higher the initial investments and costs, because you need a more capable system, you need more functionality, and that costs money. Of course, if you impose higher availability related requirements, you also raise the cost bar, perhaps on the investment side, but more on the support and reinvestment side. If you want to keep the system at a certain availability level, you must be prepared to provide a sufficient budget for this. You must support the system adequately, you must reinvest when it's time to. And there are also the other types of investments that drive requirements that drive cost. Another thing which is important to understand, that SEC is also not defined by the system itself. It's given by the scope and ambition, but it's also highly governed by the decisions taken or the decisions made, the strategic management decisions. We own this cost picture. We own the cost associated with the picture, and it will be the result of the decisions we take regarding the system. So we can control this through our requirements, but also through our decisions. So to summarize, what the mission demands, if you really want to take on this responsibility to form, develop, and sustain cost-effective systems, we must shoulder this through life responsibility. We must not put a blind eye to this right-hand side, which is now grayed out, but will soon be visible. We must take responsibility for these through life factors, integrate them into the equation, discuss them, try to assess what implications do our decisions regarding requirements, design, whatever decisions we can take in a certain program phase, what implications do they have on these through life factors? What will be the effect on availability performance? What will be the effect on the total cost picture? What will be the implications on support and sustainment? Because if we don't factor in these questions or these elements into the equations, we could get to the wrong conclusions, and we can guide the program down the wrong track. So we must include this right-hand side in the program project scope and do our best to try and analyze and illustrate and assess the effect of our decisions and how that guides us to the deliverables that we leave behind us after a project is done. It should be screened, it should be scrutinized also on this life cycle perspective side of things. And of course, we should take on this responsibility in all phases. We can never say we're done, because all the time we need to, oh, is this the right type of system for the future? Is this the right type of system for support? Is this the right type of system for a total cost minimum? We should take on this question in all phases and from the start. And this picture tries to illustrate the importance of taking on this picture early. We must shoulder this through life responsibility already from the start of a program when we conceptually discuss the capability or the system, because in these phases we set the cost bar, we set the cost level that we commit to. If we want this, if we require this, then we have to accept that the cost level will end up at a certain budget level. This is the total amount of money that this capability needs through life in order for us to reach the ambition we have set forward. So we commit strongly. After maybe the conceptual design phases, the specification requirements phases, we are more or less committed to a certain cost level. If we don't take on this responsibility, there is a high risk that we have set the program on the wrong track, that we have set the program on the wrong trajectory. We may not visualize this, we may not understand this, but it will become evident later. So if we have no control, if we have no understanding of what will the future bring to this system, how much will it cost us, then we are kind of blind to these important questions, because they will surface later. It's when we deliver the system, when we use the system, when we maintain the system, when we support the system, then it will become evident what it would really cost us to reach the ambition and have a system that can really deliver what we expected and what we originally wanted. Unfortunately, money is not infinite, so many times this overshoot in budget needed results in a failure to really reach the ambition. Many times you have to reduce the ambition, you cannot receive the full value from the system, and you have to accept that we hope for this, but what we can deliver to society, the type of needs we can meet are actually on a much lower level. So to summarize this introduction, this through life responsibility, it amounts to a commitment, hearts and minds or directives that should be there in the programs, in the projects, that we must take responsibility for these through life or life cycle issues. The management and the decisions should guarantee and strive for cost effectiveness, but it should be a cost effectiveness defined where also these future characteristics, the future behavior of the system is included in the definition of cost effective. And as I said, a part of being effective is that you can actually be available for use. The availability, performance, and the characteristics of the system in terms of its availability and cost associated with keeping a certain availability in a system, that is very important in claiming that the system is really effective. There are other factors, but availability performance is important. And of course, cost should then involve a total cost picture. If we just define cost to be some initial part of the cost picture and the other is a huge unknown, well, then there's a high risk that the decisions are not clearly on taking the right directions. So we should try to include the cost for operations, maintenance, support, sustainment, reinvestment when we discuss cost effectiveness. And as I also illustrated, we cannot talk about cost unless we have a balance scale, unless we talk about what can we get from the system. This is what it will cost if we reach a certain ambition or a certain level of operational requirements. Cost without any value associated with the cost is kind of like, it doesn't mean anything. So all the time you have to have a balance scale where you discuss cost together with the value that the system is able to deliver and take responsibility for the future behavior of the system. As this picture illustrates, we want to try and assess and understand what the future is expected to bring. So strategic analysis are required. We cannot just monitor and measure and see, oh, this was the cost that resulted. We have to have this foresight, this predictive approach to these questions. We need to use strategic analysis and try and assess, well, if we take this route, if we make these decisions, this is the expected future that we will meet. So what is the future behavior and cost that we can expect given that we take this way forward? And what type of information is needed to accurately describe the future of a system? And which are our decision variables in different stages of a program? And this leads us into this picture, which I think provides a very, very strong definition of the intended or kind of the playing field for Opus Suite. Opus Suite is intended to provide good support for conducting this, we'll say, essential or extremely required analysis really to guide a program on the right track. And there are certain types of information that is needed to describe what do we expect to see in the future. And part of the equation or part of the information deals with the RAMS properties of the technical system and the products that form the technical system. These properties define the need for support, the rate of disturbances, the reliability element of the system, the maintenance programs, the scheduled maintenance that is associated with the systems in order to try and mitigate reliability and bring a reliability to preferred levels. Then the maintainability, how do we plan to maintain and test the system to really understand what type of maintenance is needed and how do we conduct that maintenance? And then the task requirements. Well, if we want to conduct these tasks, that we will need certain resources and we will consume certain commodities, perhaps. So that's very important information. On the operations side, of course, the need of this support that is generated from the system depends highly on the type of operations that we plan for the system. How many systems do we plan to have in operations? Are they all at one place or are they deployed across the world? How are they utilized? In what environment are they used, and so forth? That will highly influence the need of support generated from the system. On the right-hand side, we see the support system, the definition of, okay, these volumes of support, these volumes of maintenance that we expect to receive from the technical system in operation, how do we plan to provide the capability for this? How do we design the support system? What maintenance concepts do we set up? What actors are involved? How do we supply spare parts and commodities that are used and needed for the operation and support of the system? How do we dimension the supply chains in terms of safety stock of spare parts, and how do we dimension the resources needed to conduct maintenance at various locations? So there are a lot of design variables there in the support system design. Then, of course, the purpose of strategic analysis is to say, okay, if we believe that the operations is like this, if the technical system and the characteristic of the technical system is like this, and the support is set up like this, what level of effectiveness or availability do we expect to reach? If we are not happy, we need to improve on some element, maybe strengthen support or reduce the need of support, to change the operational concept and the ambition for the system. But at least we need to understand, okay, what level of system effectiveness can we reach if we decide on the system in this way? What is the value delivered from the system? But equally important, the cost side. How much will it cost to keep the system at this level? We must provide, we must do the maintenance, we must provide the spare parts. There are a lot of costs that we commit to. So unless we provide these services and these resources in the support system, and we will not stay on this potential availability level. So we must understand that this is the cost if we want to keep the system at this operating around that gray point, for example. And when we have this picture, of course, we can try to guide the program and the decisions in the right way. We can do the right types of trade-offs, understand maybe we should put a little more emphasis on this factor, maybe we should stress or try and improve on a certain element in this playing field in order to reach a better performance at maybe even a lower cost or a significant or not very much higher cost, but maybe if we can get 25% more availability for a very limited cost increase, maybe we want to take that step. So there's always a trade-off between value and cost, which I have tried to stress earlier. Now, I illustrated that picture with aircraft, but what is the system? What is the system that we are responsible for, and in which phase is this system or program at the moment? I would claim that the LCM-oriented mindset, it's applicable, irrespective of what system capability you're discussing. You can talk about the system being in the ground-based air defense in Sweden, Swedish airborne search and rescue capability, railroad infrastructure, it could be a combat training center, it could be an offshore wind power park. Of course, there are certain elements in the system that will change from depending on the nature of the system and the characteristics, but you can still apply an LCM-oriented mindset. It's very general and it's still applicable. You can also apply this mindset irrespective of phase. You should do it in the early phases, in the specification, the concept phases. You can apply it, or you should apply it in the design and development of equipment. When you acquire or tender for equipment, you should apply the LCM orient. You should always try to accommodate for the future in the production delivery and in the sustainment phase. But of course, also here, the nature of the questions and the design variables at hand will differ, but you should always try to take on this, okay, what does it bring to the future if we change something here, if we change something here? All the time we should try to do our best to provide as much capability for the buck as possible. So hopefully now you think I will cover this little picture here. All of these 5 systems, there are plenty more, and all of these phases in 30 minutes, and I have to disappoint you that is clearly not feasible. What I can give you is later this year, this autumn, I will give you the Executive Lifecycle Management course here in Stockholm, which is a 3-day course held here in Stockholm and on site, and it gives you a much more time and opportunity to get a much broader picture of what this lifecycle management mindset means and how it should be introduced for a certain system in a certain phase, what type of methodology is available, what type of analysis are key in certain phases, and so on. But what I would give you now is an illustration, a quick walkthrough of two examples which I have personally been involved in. And one is tendering of combat training capability. So it's one of these systems in a certain phase. When we want to tender, we are now on the supplier, the manufacturer's side, and we want to win a bid. We want to meet customer expectation, deliver to the customer something which he will buy, but where we also take strong responsibility for the future behavior of the system. Another is the airborne search and rescue capability in the sustainment phase. And this is an illustration what type of analysis, what type of work process is needed on the user customer side in the sustainment phase. So to begin with the first case or example, I'd like to reiterate or redefine or show to you this ILS definition. This ILS, when I started with the lifecycle management, I was at Virginia Tech in '92, and integrated logistics support was kind of the key word. And it was defined by DoD that it should be used and applied in major defense programs. And what does it involve? What does ILS truly mean, according to its initial definition? Well, it's a disciplined, unified, and iterative approach to the management and technical activities necessary to integrate support considerations into system and equipment design. So we must understand the need for support that we design into a system if we design it in a certain way. So that is kind of the left-hand side. What need can we expect to get or is generated from the system if we make or design the system in a certain way? Secondly, once we know that, we should understand what it takes to form a support system, to design a support system that is strong enough so that we can meet the operational requirements. So the combined effect of the need and the capability should reach the operational requirements. And here, between these two dots, these two items, the 1 and the 2, here's where the iteration takes place. We cannot just design the system and then ask for support. We should iterate and we should review the system from this support perspective before we reach the final design review point in time. So this is often illustrated as some kind of cyclic process where we continuously cycle between system design and support system design, product design and support system design, until we reach something which is cost effective. Then when this iteration is over, we should, of course, establish the support system. We should provide the required resources, we should set up the system, the support system, so that we can actually start to deliver, and then we should deliver or provide the support. But all of this should seek a minimum cost. So, and this means a minimum LCC, of course. So this is the kind of like definition or the hearts and mind of ILS. And as you can see, it's very, very close to what I have discussed as the LCM mindset, but it's in a particular phase. It focuses on product design and development and delivery. So it's kind of like in the early phases, and it focuses on the product development side of things. We must understand what type of support requirements follow with the product. And this is a methodology that is described in standard. There are like the DoD standards, the MIL standards from the 1388s, but there are also more modern ones like the GS 007 and the S3000L. Because ILS has been kind of like misused or changed its original definition. I've also seen now that there sometimes you talk about integrated product support, but it's close to the same definition. It's just try to recoin the term here to kind of like bring it back to what it really is, because ILS has been kind of like shifted definition of this term over the years. A core element of ILS is this process or this strategy called the logistic support analysis. And that is kind of the need side of things. That is, what will the system require in terms of support? Define and form the product RAM's properties. So there are certain elements. We must describe what the product is, a product breakdown, what are the components. That's sometimes called the design interface. Then we have the reliability element. Okay, now we know what the product looks like, at least on a piece of paper. What type of reliability, what type of failure modes? How can the product fail? What will be their functional effect? What will be the criticality? What will be their frequency? Are there any aging effect in these failure modes? Will it be more frequent after a certain time of usage? And so forth. This is often called FMECA, but FMECA is really a methodology for trying to assess these reliability-related questions. Once we know the reliability, then we can start to ask ourselves, maybe we can moderate or mitigate this tendency to fail by imposing scheduled maintenance programs. Are there any failures, any failure modes that we can prevent? Fully prevent, or maybe reduce the risk of? Maybe we need to do inspections to check the condition of certain components. So we need to set up a scheduled maintenance program to see what should be done and how often. And of course, in order to try and mitigate the reliability. And the term used for this is often reliability-centered maintenance, because all of these scheduled activities that are imposed should, of course, have a positive effect on the reliability of the system or the product. Next, we also need to discuss the testability and maintainability elements of the product. And this is often called M&T, the maintainability and testability elements, and that discusses, okay, when there is a failure, how do we understand what has happened? What type of procedures, what type of measures for diagnostics do we have at hand? Are they going to be built in, or are they going to be conducted through external tests? So we need to set up test procedures, have test equipment, or we need to equip the system with built-in test facilities or components. So we can understand and assist the maintenance that, okay, this is what had happened. This is the maintenance task you need to do in order to restore the functionality of the system. And then, okay, what type of maintenance tasks do we then need to do? That could be a sequence of maintenance tasks. Okay, remove and replace, maybe repair, discard. So there could be quite a long chain of different tasks that result when a certain failure occurs. Once we know the tasks, you can start to ask yourself, okay, if I want to do this, if I want to remove and replace this, if I want to repair this, if I want to test this, what type of requirements are placed to, what do I need to have at hand in order to conduct this task? What will be the elapsed time, but equally important, what resources are required or consumed? This is often called the maintenance task analysis. So this is kind of like the set of tasks or activities, the type of analysis you need to conduct in order to try and find the RAM's properties of the product. And once you have done this, you can form this collected piece of information, this LSAR, the Logistics Support Analysis Record, which is basically the answer to these questions in a prescribed format. So this is like this very important element of ILS. Try and find this description of the product and how it will behave in terms of its support aspects. Then you can ask yourself, well, how do I come to these answers? Is it through prediction? Is it through engineering judgment? Is it through monitoring? Is it through analysis? So there are many different means or methods to try and find an answer to one of these questions. In early phases in kind of development projects, you often have to reside to prediction or engineering judgment. But of course, the more you can use monitoring, experience data, practical life experience, and so on, the stronger you can be in your credibility or your in the accuracy of these assessments. Also, some of the questions here are more setting a policy, because it's not built into the system to decide, oh, we're gonna find out a failure this way or that way. That becomes more of a policy. Also, the maintainability is largely a policy answer. We say that, okay, if this happens, I will first remove and replace in order to restore the system, and then I will test and see what was wrong with this. Or you could say, well, I do test on the system and I try to repair in place. That's more of a policy than a data. So, okay. Once you have all of this information, this is very central information as a product manufacturer to really try and contain, structure, and have good control of. You can say this is a repository of LSA or product RAMs data information. And it's a very, very strong piece of information to have at hand. And this brings us into the case, because the case here is, it's an RFQ. There is a customer, there's a defense force in the world that wants to have live combat training capability. And we are the provider of such systems and such capability. This customer has described to us the operational requirements and the preconditions. These are the amount of training sites. These are the frequency of training programs. These are the size of a trained unit. This is the length of an exercise, the various descriptions of operations, and also regarding system effectiveness. Okay, how long can we expect an exercise to be down? How many players can be lost for a certain period of time? They describe their tolerance. The game's not 100% completion, but they could accept a certain degradation and still say that this was a good training. Then also a definition and a description of the support services that we as the product supplier are expected to provide, and a contract length. So the customer here has very nicely, or I would say very accurately described to us what is it really that he wants in terms of capability. He wants to be able to train soldiers, and we should provide the technical infrastructure to deliver this. This defines for us the type of products that we need to deliver. We need a communications network at each site because it's based on communication between different detectors and lasers and an exercise and control center. So we can really monitor and see what happens in this exercise, who shoots on whom. There are core training equipment, there are these lasers and detectors, there are personal equipment that you have on yourself, on your helmet, or so you can see if you've been hit, and then you have weapon mounted and vehicle mounted. So these are like core training equipment. And there are some auxiliary gadgets like sound and smoke that are there to try and imitate a more realistic battle environment. So we have a clear picture of what we are expected to deliver product-wise. And what is very nice is that we have good control of these support-related aspects of the products. All of these products that are part of these product packages, we have good information concerning their support characteristics. So now we want to start and prepare our bid. We are in this bid preparation phase, and we have now set up a work process where we can use this information and appropriate analysis to try and say, okay, this is how we should prepare our bid. This is what our bid should be in order to control the cost, minimize the cost, still reach the customer expectation, and make money from this. And what we can control is basically the support side of things. The products are already defined, they're already designed, so that's more of like a set cost. Okay, if you want to buy this amount of products from us, we have a more set cost picture. They are not developed, they are more consumables off the shelf, but the support services we can definitely influence. So decision variables are largely related to how do we define the support based on this setup. So support system design becomes the main variable, the main degree of freedom that we can control in this bid preparation process. So we can use our tools here in Opus Suite to get a good control of this. And we have the set of products. They're going to be continuously used. They're broken down into components and sub-components. We have failure modes. We have failure rates, we have maintenance procedures, we have tasks, we have everything in this LSA or repository. Now we have the customer case. We have a baseline operations and support concept. We have set up, okay, he wants these 4 sites where he wants to be able to conduct battle training. We have proposed a maintenance and support concept for this. And also there are certain cost elements that we want to assess. So how much does it cost to provide an extra spare part? How much does it cost to provide labor and material to conduct corrective maintenance? What is the cost of the spares being consumed? Could be other cost elements. But all in all, we can then rather straightforwardly come to an analysis here and say, okay, with all of these pieces of information readily available, we can start to assess, okay, for a spares investment of a certain amount of money, we can reach a good enough availability on the products. And a 99.5%. Perhaps this is enough to reach the stated operation requirements, but I would say that the mean downtime of 2 hours here is also important. Maybe we can stop an exercise, or we can lose a product for 2 hours and still be able to have the training ongoing. We can also have a look at what is the annual costs. So this was to set up, but also to operate, and it's about 1 million per year to provide this corrective maintenance and to cover the spare consumptions. Of course, we could add other cost elements. We can also look at the maintenance and transport volumes generated, so we can start to assess the required capacity and the utilization of capacity, so we have a good balance between what we must have as capacity and that we use it, so we don't pay for unused capacity and so forth. All in all, we can rather quickly start to assess what is the best support bid, or the best bid we can prepare for this customer. So the case summary here is that this supplier is very, very ambitious and very mature regarding this ILS question. He already has good control of, well, he has a strategy. He has in the work process that when we are supposed to bid, we must take control of these crew life aspects. So we have it in the strategy. We cannot leave a bid. We cannot present a bid without having assessed and scrutinized these crew life aspects associated with the bid. We have good control of the information through this LSAR repository. We have the correct type of tools that can quickly give us answers and indication and guide the bid in the right direction. So we have all of these three cornerstones of LCM in place. The next case is, I have to move on quickly now. The next case is in the sustainment phase, and it illustrates what is sometimes called the fracas loop. So when you're in sustainment, the most important question to ask yourself is to understand, where are we? How much money have we spent, or do we spend on this capability? And what type of performance do we get at the moment? What is the availability? What is the effectiveness? What is the value that the system can deliver? And perhaps ask yourself, this is perhaps not where we want it to be, or where we hoped or planned to be. There could be some kind of a rather large deficiency between effectiveness and where we're actually operating, or cost and where we're actually operating. And of course, what are the reasons for this mismatch? Why are we losing value effectiveness from the system? Why are the costs higher? Trying to assess that these are the main drivers and reasons for not being where we hope to be. When we see this, of course, we should start to discuss corrective actions. Are there any corrective actions that can help us to regain some of the lost value, increase the value, effectiveness, availability? Are there any actions that can help us reduce the cost without perhaps dramatically changing the level of availability, but preferably both? Are there any corrective actions that will really improve on both aspects? And there could be. And this is the meaning of fracas. Failure reporting, that we should monitor the system and the cost picture. Analysis, that we should assess the reasons for being where we are, assess the effect of the different corrective actions. So the corrective actions, we should assess and analyze them and establish and implement them to try and bring the system to a better state. And the system in FRACAS means that this should be a recurring activity to support strategic program management. So FRACAS, the FRACAS loop. This should be an ongoing activity that we all the time try to conduct in order to try and bring the system to the best possible state. The case here is taken from the Swedish airborne search and rescue capability, which is the head authority for this is the Swedish Maritime Authority, and they should provide nationwide coverage, both land and sea. So they should be able to conduct search and rescue missions irrespective of weather conditions 24/7. So that's kind of like the definition of the capability that they must provide. To be able to provide this capability, they have a fleet of search and rescue helicopters. Currently, they own 7, and they were introduced around 10 years ago now. They are in operations and support phase or in the sustainment phase. Of course, they want the society wants high readiness and ambition. We want to be able to meet this nationwide coverage 24/7, irrespective of weather conditions. So we need to have a higher helicopter availability, limited downtime on the helicopters, and a low and attractive cost picture. That's also, of course, always interesting to try and reach these requirements at a reasonable or attractive cost picture. So the preconditions here, the definition of the system here is shown in this picture. The ambition is to keep 5 bases at the bottom of this picture with 1 fully operational helicopter. We have 7, so we should have 5 allocated to the bases. There is on average 1 in scheduled maintenance or base checks at SMA maintenance, the base maintenance capability in the middle of the picture. We should hopefully have 1 as a backup, which can step in if we have unscheduled downtime on one of the base. And then we have the suppliers that can help us to repair components, maintain components, supply components. The utilization is about 400 flight hours per helicopter in year. And that is the reason why we needed 2 base checks per helicopter in year. With this amount of flying hours, we need to bring in the system for safety inspections, base checks twice per year. So that's why we need to have time to have at least 1 in base maintenance over time. And the maintenance concept with us, which I said, is that we're going to have these time-consuming base checks in the middle of the picture. If there is unscheduled corrective maintenance, we can sometimes do it down at the line. Sometimes it's conducted at the base. So that's on helicopter, but off helicopter or component maintenance, that is contracted and done by suppliers, which also supply us with discardable components. So the capability management here, we have assisted them since 2017 with this FRACAS loop, this strategic SAR capability management from the Systicon side. And we try to help to sort them out. And the first project we started was, okay, what do we need to do in our support system to improve or lift the helicopter availability? So we worked on the right-hand side there. Second one was on the left-hand side. Do we need to increase the fleet of helicopters? Are there any system design changes, any modifications to the systems that are needed in order to try and bring the system to a higher availability, higher readiness? Another one popping up like 3 years ago was, okay, if there are some disturbances in the support and the supply of components in the supply chain, how should we try and provide better robust readiness, better robustness against disturbances? And finally, the system lifecycle plan, where we did not only focus on the availability element, but also on the technical performance element and say, what does the system need to be in order to improve for the future? But now I will illustrate this third topic, this third part of the FRACAS loop, which we conducted 3 years ago. So robust readiness. The background for this was that, okay, through this 2017, 2019 projects, they felt that they were now reaching a satisfactory level of readiness. They could keep these 5 bases with 1 functional helicopter most of the time. But they were heavily reliant on these foreign suppliers. Most of them were abroad, and Leonardo helicopters were dominant. So they needed to make sure that they had good access to these suppliers. But it was a cost-effective means to provide this component maintenance and supply. They needed quite a limited stock within the organization because these contracts were strong enough, so they didn't need a lot of safety stock, given that they had access to these suppliers. But in 2020, Corona struck. And the question was that, okay, it's working now, but what if we lose the suppliers? What if there are disturbances? How long can we endure if we lose some or all of these foreign suppliers? How can we cost effectively improve our robustness, and what investments are required and motivated to try and bring a better security of supply in place? Because it was a lot of just in time, now we need more of a just in case. And of course, things that have happened after 2020 has further strengthened or underpinned this need to have better security of supply. The war in Ukraine, the Suez Canal incidents and so on. So this has been kind of like moved back into the equation now, that we need to have this element of self-sufficiency. What they believed they were operating around when they were into 2020 was around 95% spares availability. So most of the time they didn't have the spare, but they sometimes were waiting for a spare component. So they had about 5% of the time one helicopter grounded, or a helicopter grounded because they needed to wait for a spare. But you cannot have 100%, so this was believed to be cost effective. But they sometimes used robbing. They sometimes borrowed from a base check helicopter. But of course, this was not good, and they wanted to limit that. But still, they were quite happy with supply in this kind of like peacetime scenario when they had the supply chains up and running. But if the supply chains were disturbed and they were cut off from suppliers, of course, they would start to rob or cannibalize because the supply is off. So the best they can do is try to concentrate back orders, use the grounded back orders as donors, and try to find whatever parts is available within the fleet. And we therefore developed this cannibalization model, which is an extension to the classic Opus model, but it was very important here because in this scenario, when you lose your suppliers, you will start to cannibalize across the fleet. So we could start to analyze this with Opus 10 then, mainly. So we looked at, okay, this normal production, these normal conditions, when we don't use cannibalization or don't want to use cannibalization or robbing, do we have enough stock? And it showed that, well, this robbing sometimes needed to step in. So there was a motivation to increase the stock within SMA. But it was a very minor increase needed to bring even better coverage and reduce the need of this type of robbing activities. So, okay, with the 7%, around 7% of the annual support budget, we can greatly improve on our spares availability and reach the 95% without any robbing measures. Okay, good. But then the question was, what if suppliers are cut off? What if this endurance situation happens? Assume all suppliers are cut off and we start to cannibalize. The central question then becomes, how rapidly will our spares availability drop, the helicopter availability drop, and our readiness level drop? How many bases can we equip after, for say, 90 days with a functional helicopter when we lose access to our suppliers? Of course, we used the cannibalization extension for this. And we looked at this picture, produced this picture. So we see that, well, if we aim for around 90 days, with the current stock, we can equip 2 bases after 90 days on average. With a boosted stock, 3 bases. But this was not really what was hoped for. Maybe closer to 100 or 5 bases equipped. But of course, this costs money. So we need to say that, okay, conclusion is that, well, there's room to even improve here and add stock in order to provide a better tolerance against say, 90-day cutoff. So we started to look at this and say, well, if you buy stocks so that you can cover 30 days without any drop, if you cover 60 days without any drop, if you cover 90 days without any drop, you can see the yellow, the red, and the blue lines here. Of course, you can improve your tolerance. And if you buy for 90-day coverage, yeah, you can expect to have all your current performance there up and running, but it will be very, very costly. So now we need to start to trade off between your ambition and your cost. And but once you see this picture, you say, okay, what are we happy with? And the conclusion was that if we aim for this coverage, full coverage for 30 days, then together with cannibalization, that would provide quite a good coverage even after 90 days. So about 4.5 bases on average could be equipped with a helicopter. And that needed quite a reasonable budget. So that became the kind of like final answer. So to summarize here, what is good with this organization is they have good LCM orientation within the managers and the management. So they want to conduct this strategic analysis to help them in their capability management endeavors. So they understand the strategic decisions. They want to use strategic analysis to try and sort out the best way forward. In this illustrated case, how to ensure your robust readiness. In this case, we could also operate, this is in the sustainment phase, we had good access to follow-up information and hard facts. They had failure rates, they had experience data, they had the lead times, they had all pieces of information that was actually actual data. So we could use all the pieces of information from reality, which is good in the sustainment phase. And we could provide the required type of analysis to sort out that this is the cost-effective decisions, this is what you need in terms of budget to reach an improved performance. We used the Opus 10, but we also extended it with this cannibalization feature. And this shows that also in this sustainment phase, you can have, even as if I said that, well, you need to bring the system on the right track. Of course, you can correct also and make strategic improvements on the system also in the sustainment phase. And you must, and you should, all the time try to take this strategic perspective on things and say, okay, this is what we need to do in order to improve. So this is to summarize. Sorry, I had to speed up there by the end, but I see I want to reach about 1 hour, but I can point you to this possibility to take on the Executive Lifecycle Management Program. And we have a planned date for this now, September 26 to 28 this year in Stockholm. So if you feel that you want to have more chance, more time to discuss, more time to dig deeper into this topic, please check this page out and perhaps hopefully register. So question and answers. I see here on the question list there are some questions. I see if I can find something. There's one here. I think it's fair to say that sustainment of mission success is underpinned by sustainment of availability of capability and support balanced by the through life cost to achieve this. However, a significant influence on this goal is the question on when an assumption becomes a decision. Often we capture decisions in a master data assumption list, but we should capture the decision as such and identify the decision owner. I would say this is more of a comment than a question. So I thank the submission of this question, but I don't disagree, but I don't think I can comment anymore on this. So I think we are really reaching the end here, and I foresaw that 1 hour should be very compact, but we managed to reach at least what I hope to cover in this hour. So hopefully, if you found this interesting and you want more time to dig into it, hopefully we can meet in real life in September. And with this, I thank you very much for listening in. And yeah, thank you.